Hello and welcome to the course Signals and Systems. I am Dr. Zishan Karim from Electrical Engineering Department, CUIWA campus. In this video, we will discuss the topic difference equation. As we already covered the differential equation for the continuous time system, whereas for a discrete time system, we will cover the difference equation. And second topic which that we cover in this video will be the system representation by a block diagram. So, what are the difference equations for discrete time system? Different discrete time analog of a differential equation, the king of computation for system outputs. For example, you have the system with the transfer function h, and xn is the input and the yn is the output. So, for a discrete time system, we can write the system in terms of a difference equation in this way. This is the output signal, and whereas these are the inputs, these are the output signals, but with some delays. For example, n1, n2, n, right? And on the right hand side of equation, we have a input of the input to the system, and with the coefficients b naught for the index for n and b1 for n minus 1, and so on up to bmxn minus n. And when we combine this equation, we can write in this way: summation k equals to 0 to n, because there are n number of terms, right? And ak is the coefficient, and y n minus k. So we will iterate with respect to k, and l will remain constant. So from k to capital N. So for yn here we have a naught equals to 1, right? So the coefficient we take here beside the yn is 1. So equals to k equals to 0 to capital M, because there are m number of terms here, bk x n minus k. So this is our input, and this is the combination of outputs, right, with some delay as well. So this is nth order. So n plus m plus 1 parameters, because there are m terms, n term, and plus 1 term. Which is plus 1 term? The 0 term is plus 1, right? Completely define the system. So computation, as you know that for any system we need to find the output, right, which is yn here. Previously we found the output for the continuous case, which was yt. Here we are focusing on discrete time system. So for to find the output, we will rearrange the equation. So yn, if we separate yn, look at this equation. If we separate yn, so these all terms will become negative on the other side. So if we sum them, right, in this way, right, because we change the index from k equals to 1 instead of k equal to 0 here, because we separated the term yn. So yn equals to k equals to 1 to n with the negative sign, ak yn minus k. These are the past outputs. This is the present output, and this is the past output, and these are the inputs, right? So this is the representation of our difference equation, representation in terms of a difference equation for a discrete time system. Okay, let's take an example to look at how we can deal with the LTI system with difference equations. For example, we have a system that can be represented as yn minus half yn minus 1 equals to 1 by 4 xn plus 1 by 4 x minus n minus 1. These are input side, this is the output side. These are the past outputs, and this is the current output, right? So let's first rearrange them, because we need to find the output y of n, right? So after rearranging, this term will move toward the right side, right? So we can get half yn minus 1 plus 1 by 4 xn plus 1 by 4 x minus 1. Let's start with n equals to 0. N equals to 0 means you know that the first term, right? So when we put n equals to 0 here, so y0 half y minus 1 plus 1 by 4 x0 plus 1 by 4 x minus 1, right? And now this type of situation is called the recursive equation. This type of equation is called recursive equation. Why is recursive? Because you know that you can see that y0 depends on y minus 1. So this is one kind of a previous output, right? So when you calculate similarly, iterate and find the other term. For example, if you put n equals to 1 here, so y1, so y1 depends on y0, and so on. For y2, when we go further, it depends on y1 as well. So this will continue. So it is called a type of a recursive equation as well. And in MATLAB, if you implement this, so we can use the command filter. So filter in MATLAB is the type of a command which can help to find the solution of that equation, right? Suppose that xn, we have an input value which is 0 for less than 0, and for greater than or equal to 0 it is 1, right? So and we have an initial condition of y minus 1 equals to 0. It means that it is initially at rest. When we don't have a output before input, so it is when it is output is 0, it is called the initial rest, which we already discussed in the previous lectures as well. So let's calculate y0. For y0 half x of 0, for y0 half y minus 1, if you see this equation, y minus 1, so y minus 1 is 0, so put 0 here, and 1 by 4 x0. What is x0? At 0 x0 xn is 1, so put 1 here, and for 1 by 4 x minus 1, where x minus 1 means for less than 0, which is 0, so put here. So we get 1 by 4. So continue calculating this one. For y1 we have a y0 here. So y0 we found from here y1 by 4 and carry on. So we will get 5 by 8 and so on. So in this way, this is kind of a recursive equation, and we find the solution for different value of n, right? Okay, there can be a number of different types of impulse responses in the system. So first, before going into that, we discuss the causal system. This is the general convolution equation which we already studied, that yn equals to k equals to minus infinity to infinity xk x and minus k. So this is a convolution equation. So if we further evaluate or open this equation, we can see that, notice that there are terms h minus 2, xn plus 2, h minus 1, xn plus 1, x0, xn, so on. So from minus infinity to plus infinity, right? But for a causal system, if you want a causal system, then you know that there should be no output before the input, right? This is called causal. So for n less than 0, we consider hn equal to 0. So that's why these terms with the minus sign will become 0, and we only have these terms like which occurs at 0 or above, right? So this is called the causal system. Now discuss the finite impulse response. What is finite impulse response? It means that number of non-zero Hn is finite. Non-zero Hn. It means that the value of Hn with value greater than 0 is finite. There are not infinite impulse responses. For example, if you give the system an impulse, then the output should have a finite value of response Hn for that input. Not there should be infinite number of responses. For example, most common form of Hn equals to 0 for n less than 0 and n greater or equal to n. It means that now for n less than 0, we always have a impulse response value 0, and for n greater or equal to n, capital N. What is this n? We will see this is the number of terms, for example 1, 2, 3, so on, for which we are interested to find the output. So this can be a number, any number, right? So for this, if we have a number greater than n, then this impulse response will always be 0. So it means that impulse response will lie between n equals to greater than 0 to greater or equal to from 0 to n, right? It means that something you have always impulse response from 0 to n, but from above n and less than 0 it will always be 0. Let's take an example. For example, yn equals to k0 to n minus 1 hn xn minus k. So when we open this one, h0 xn h1 xn minus 1, so it will iterate till n, right? So hn minus 1 and xn minus n plus 1. So there will be always limit, not infinite. So this is kind of a finite impulse response type of a system, right? And let's see, take an example where we have a x0 and h1 two terms, right? And both are half, whereas hn equals to 0 for n not equal to 0 and 1. It means that we have a two terms and output will be for two terms only, which is h0 and h1. So half xn plus half xn minus 1, whereas we can't see another higher order terms after that one. So this is the shape of a finite impulse response of a system, right? And another one, this is infinite impulse response. So what is infinite impulse response? As we already studied, we have a, when hn we have hn uh, impulse response is 0 for less than 0 and for greater than capital N if it is 0, then it is called finite impulse response. On the other side, if we have a for n greater than n, we have always have an impulse response. So it means that the system is infinite, has infinite number of responses. So we call or we know name them as an infinite impulse response, right? Let's see the example. Hn equals to 0 for n less than 0, right? This is similarly as the finite impulse response. Whereas for n greater or equal to 0, uh, it, it is always half n. It is not going to be 0. So it means that when impulse response is not going to be 0, it means it is infinite. So we can't compute convolution sum for infinite impulse response systems. As we calculated the convolution sum like this sum for the finite impulse response of a system, right? But if we have a IRR systems, infinite impulse response, we can't calculate this sum. So how can we calculate the output in this case? In this case, we will use the difference equation for output. So this is our difference equation, uh, which we already studied. K minus k equals to 1 to n, a k y, n minus k, k equals to 0, so on. So if we input xn, which is impulse, you know that impulse response means you have to input the impulse, right, at delta n. So how it behaves. For example, if you put ak equals to 0, ak distance, ak equals to 0, these coefficients are 0. When these coefficients are 0, this one, it will become a finite impulse response system, right? Because in finite impulse response, you don't have an output before input occurs. So we don't have a past outputs before the inputs, right? So this term will be 0. Whereas if we don't have this ak equals to 0, we don't have a ak equals to 0 for any term. For example, a1 its term is not 0. Then we have a recursive type of equation, and when we have a recursive type of equation, then this is named as a infinite impulse response system. So for any recursive system, if we uh, for any type of recursive system, these are called also called an infinite impulse response system as well, because this term will not be 0 for infinite impulse response system. So in this way, by using difference equation, we can compute the output for a infinite impulse response system as well. Okay, now find the impulse response for this equation. So the question is, we have to find the impulse response Hn of this system. So To find impulse response, the input should be impulse, right? You know that. So let xn equals to delta n. So put delta n here. So hn equals to half hn minus 1. So instead of yn, you have out when you input the impulse, then output is named as impulse response. So in terms of y, we replace y with hn, and for the yn minus 1, we replace with hn minus 1. And for input, we have a delta n. And you know that if system is causal, then hn is 0 for n less than 0, right? And whereas for x0, when we put n equals to 0, so for n equals to 0, this delta n equals to 1, always 1. So we have a input 1 and half h n minus 1 as well. And for n equals to 1, we have a half h0. So it means that this output that we calculated here will be used here, and plus 0, because for delta is always 0 for other than 0, right? So it is half equals to half, because we already have a 1 from here. So put 1 half into 1, which is half, equals to half. Then h1, so for n equals to 2, we have again h1 here. So half into half, which becomes 1/4. So output will be 1/4. And if we carry on, it will become half hn equals to half raised to power n. So it is dependent. If we increase the n, it is not going to decay, so completely 0 for n, right, for any value of n. So it means that we have an infinite number of terms if we carry on. Although it will be very small terms, but there should be some output as well, right? So for n greater than 0, so this type of system is called infinite impulse response system. Let's move to the topic signal representations by block diagram. Now, how can we represent a signal or a system with a block diagram? What are the benefits of representing a LTI system in terms of a block diagram? The main benefit is that it's easy to solve equations because of pictorial visibility. As we are looking into the equations in a sense of pictorial way, so it will be easy to solve that equation as well. And it can be easily input to the analog and digital systems, as we have a complete pictorial view, so we can easily input to that in analog and digital system as well. And it is easiest way to represent the whole differential equations, which can help to implement in hardware. So when we represent them in a block diagram, so as complete block diagram is in front of us, so we can easily implement that in the hardware. So examples of multiple inputs with inputs u1, u2 and output y. For example, if we see the summing system, then we have a u1 as an input and u2 is another input. So we sum up here and we get the output y here. So this is kind of a summing system. And difference system, we have a u1 here and the difference sign, negative sign here. So we will get the y as output. Similarly, for the multiplier system, we have a multiplication sign here and we get the multiplication output of the system. So on. Okay, let's take an example of a differential equation and of an equation and have two difference equation. We have to represent them as in a terms of a block diagram. So yn plus a yn minus 1, right, and b of x of n. So first of all, we need to find, as you know, that we have to find the yn from this equation. So we have to rearrange. So after rearranging, we will get minus sign here. So minus a(y)(n) minus 1. This is the first output, and the bx of n. So by seeing this, we need what kind of block we need. So uh, we require the blocks of addition, right, and the subtraction. Addition or subtraction, and kind of a delay to implement this one, right, and the coefficient multiplier, for example a(y)(n) minus 1. So first, for example, x1 and x2 and here, so this is the kind of summation. So x1 plus x2, and if we have a block where we have a multiplier, so xn into a, so we get axn. Similarly for the b xn we can get b xn, so on. And for the delay we have a block which implement the delay. So if you input xn here, you will get the delayed version here, xn minus 1. So these are some basic components we need to implement this equation. So let's implement this equation now. So xn, for xn you have a b here, right? So b xn, so multiply by b to get bxn here at the input, and from output it is called yn. So when you pass this output from a delay, so you will get one time delay here, yn minus 1, and for delayed you need a coefficient which is minus a, so minus a yn minus 1 when come here, so it is a adder block, right, addition. So we already have a bxn here, so minus a yn minus 1, so we get yn equals to minus a yn minus 1 plus b x of n. Similarly, we can implement the other equation as well in terms of the discrete time system. We can implement in terms of block diagram. This is another example where we have a differential like dy by dt, a by t, b by xt. So we, as you know, that we need the output which is yt. So rearrange them. So after rearranging, we get b over a, sorry, minus 1 over a dy over dt plus b over a xt. So here we need the block diagrams. The components to create that block diagram is, one is the adder as before, one is the multiplier as before. We have coefficients here like b by a minus 1 by a, so we need multiply. And the additional one is the differentiator, right? Because we have to differentiate as well. So xt dxt over dt. Now let's implement in terms this equation in terms of a block diagram. So similarly, as you know that yt, so when we plus the yt from the differentiator, we will get dy over dt here. Then we need a multiplier which is minus 1 by a to get this equation, right? And afterwards we need a sum right here, and uh, before summing we need a multiplication of b by a with xt. So we have a multiplier of factor with b by a here. So in this way we get the output yt which is equivalent to this equation, right? So this was the representation of this equation. But the problem here is that the differential equation or the differentiator is usually complex in implementation, and it is very much sensitive to error. So to overcome this sensitivity, we can switch to the integrator. So let's solve the same example by using the integrator. Okay, the solving the same problem after rewriting as in integral form, because usually the differential operators, as I mentioned, are difficult to solve and has the high complexity. So we have equation this one. So we represent to represent this in terms of integration. So first rearrange them. So dy by dt and differential term on the left hand side and equivalent to bxt, because the right hand side we have a bxt minus this term will move this side, so minus ay over t, and then integrating from minus infinity to t. Now we have to take the integral on both sides, right, and this side and on this side. So if you, and the limit of this integral is minus infinity to t, so minus infinity to t minus infinity to t. And if you take that integrator, integration on integral on the left side, so differentiator and the differentiation and the integration will cancel out and we will get yt here, right? And for this one minus infinity, we have a equation minus infinity to t bx of t minus a yt dt or d term. Why it is yt only, the limit minus infinity? The reason is that we have a causal type of a system, and we know that before 0 there is no output. So since the value of minus infinity is 0, so we have a causal type of input, so we obtain y of t equal to this one. In this form can be and you can see that this one can be implemented by using the adder, because this subtraction sign can be used by the adder, coefficient multiplier, as we already discussed, together with the integrator. So we need the additional term, which is integrator. Thank you for listening, and for question answer there will be a separate session which will be communicated later on. Thank you very much.